What specific problem does the proposed method aim to solve?
The proposed method, Phased Consistency Model, PCM, aims to solve the limitations of existing models, such as latent consistency models, LCMs, in terms of consistency, controllability, and efficiency during image sampling. Specifically, PCM addresses issues related to inconsistency in results generated with the same seeds in different inference steps, limited controllability in image generation, and inferior results at few step settings. PCM phases the ODE trajectory into several sub-trajectories and enforces the self-consistency property on each sub-trajectory, allowing for deterministic sampling without error accumulation. By doing so, PCM improves stability, controllability, and efficiency in image generation compared to traditional LCMs.
How does the proposed method work, and could you illustrate it step by step?
The proposed method, Phased Consistency Model, PCM, works by addressing the limitations of latent consistency models, LCMs, in terms of consistency, controllability, and efficiency in image and video generation. PCM phases the ODE trajectory into several sub-trajectories and enforces the self-consistency property on each sub-trajectory. This allows PCM to sample results along the solution points of different sub-trajectories in a deterministic manner without error accumulation. Step by step, PCM first splits the trajectory into multiple sub-trajectories with defined edge time steps. Each sub-trajectory is treated as an independent consistency model. The consistency function within each sub-trajectory ensures that outputs are consistent for arbitrary pairs on the same sub-trajectory. The boundary conian is crucial for successful training, and it is satisfied by explicitly parameterizing the consistency function. PCM then introduces a phased consistency distillation objective, where the trajectory is discretized into subintervals and the solution estimation error within and across sub-trajectories is bounded. Sampling is supported by deterministic sampling, following the definition of the transition from one time step to another within the same sub-trajectory. Additionally, PCM introduces an adversarial consistency loss to enforce distribution consistency, improving generation results in low-step regimes. The adversarial loss penalizes the distribution distance between the sampled points and the predicted solution points, optimizing the distribution consistency. Overall, PCM's phased approach, consistency enforcement, and adversarial consistency loss work together to overcome the limitations of LCMs, providing stable and efficient image and video generation results.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the Phased Consistency Model, PCM method outlined in the paper include 1. Deterministic sampling. PCM supports deterministic sampling by phasing the ODE trajectory into multiple sub-trajectories, allowing for stable and consistent image generation across varying inference steps. This deterministic sampling helps preserve image consistency and quality. 2. Efficiency. PCM addresses the limitations of previous models by improving efficiency in image sampling, especially in low-step settings. By phasing the ODE trajectory and using an adversarial loss in the latent space for fine-grained supervision, PCM can generate superior results even in fewer inference steps. 3. Controllability. PCM enhances controllability in image generation by removing the need for classifier-free guidance, CFG strategies, which were limiting in previous models. This improvement allows for better hyperparameter selection and responsiveness to prompts, leading to more controlled image generation. 4. Distribution consistency. The introduction of an adversarial consistency loss in PCM enforces distribution consistency, resulting in improved generation results, especially in low-step regimes. This loss helps align the data distribution of generated images with real data distribution, enhancing the overall quality of the generated images. 5. Sensitivity to negative prompts. PCM demonstrates increased sensitivity to negative prompts compared to previous models like LCM. This sensitivity allows for better alignment with prompts and negative prompts, leading to more accurate and diverse image generation. 6. Consistent generation ability. PCM exhibits superior consistent generation ability under different inference steps, which is crucial for multi-step refinement in image generation tasks. This consistency ensures that the quality of generated images remains high across varying numbers of inference steps. 7. Stability in training. The design of PCM ensures stable training by avoiding the use of normal GAN loss, which can lead to training instability and corrupt generation results. The adversarial consistency loss in PCM provides a more effective and stable training paradigm. 8. Improved sampling. The randomness introduced in sampling with PCM helps alleviate unrealistic objects or shapes in generated images, leading to more diverse and realistic results. In summary, PCM offers a comprehensive solution to the limitations of previous models, providing deterministic sampling, efficiency, controllability, distribution consistency, sensitivity to prompts, stable training, and improved sampling, ultimately leading to superior image generation results across various inference steps.
How is the method validated or tested?
The method proposed in the paper, Phased Consistency Model (PCM), is validated through extensive experiments on widely recognized image and video generation benchmarks. For image generation, the model is tested on the COCO 2014 dataset and the CC12M dataset using the FID and CLIP score metrics. The performance is compared with other methods such as Stable Diffusion V1-5, InstaFlow, LCM, CTM, and SD Turbo. Additionally, the FID-CLIP metric is computed to evaluate the model's performance compared to original pre-trained diffusion models. For video generation, the model is evaluated on the UCF101 dataset using metrics like clip score, clip consistency, and flow magnitude. The comparison includes methods like DDIM, DPM, and Animate LCM. The experiments cover one-step generation, as well as multi-step generation scenarios, showcasing the model's ability to generate high-quality images and videos consistently across different inference steps. Ablation studies are also conducted to analyze the sensitivity to negative prompts, consistent generation ability, and the effectiveness of the adversarial consistency loss design. The results of these experiments demonstrate the advancements of PCM over existing methods in terms of consistency, controllability, and efficiency in image and video generation tasks.
What results were achieved with this new method?
The new method, Phased Consistency Model (PCM), achieved significant advancements in image and video generation. Specifically, PCM addressed the limitations of previous models such as LCM by improving consistency, controllability, and efficiency during image sampling. PCM was able to support deterministic sampling by phasing the ode trajectory into several sub-trajectories, allowing for stable and consistent image generation with varying inference steps. The model showed superior performance in both one-step and multi-step generation, compared to consistency model-based methods like LCM and CTM. PCM also outperformed state-of-the-art GAN-based and rectified flow-based methods in one-step generation tasks. Additionally, PCM demonstrated better sensitivity to negative prompts and consistent generation ability under different inference steps. The introduction of an adversarial consistency loss further improved the generation results, especially in the low-step regime. Overall, PCM showcased remarkable advancements in image and video generation, proving to be a highly effective and efficient model for stable and fast image and video generation.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method proposed in the paper include 1. Consistency. The current design of latent consistency models, LCMs, leads to inconsistency in results generated with the same seeds in different inference steps due to the purely stochastic multi-step sampling algorithm used. This inconsistency affects the stability of image generation in both few and many inference steps. 2. Controllability. LCMs equipped with weights can only accept classifier-free guidance, CFG, with 1 to 2 steps, limiting the controllability on image generation. Larger values of CFG led to the exposure problem, making hyperparameter selection more challenging. Additionally, LCMs are insensitive to negative prompts, generating similar results even when provided with different prompts, reducing controllability further. 3. Efficiency. LCMs tend to generate inferior results, especially in settings with fewer than 4 inference steps. This inefficiency is attributed to the traditional loss functions used in LCM procedures, which are not suitable for fine-grained supervision in low-step settings. 4. Stochastic error accumulation. The use of only one solution point in consistency models introduces stochastic errors in multiple sampling procedures, affecting the stability and reliability of the generated samples. 5. Training objective redundancy. Consistency trajectory models, CTMs, have a redundant learning objective, as they need to learn to move each point to all other points in the trajectory, leading to increased complexity and training overhead. 6. Dependency on CFG. The method relies on classifier-free guidance, CFG, for training, and removing CFG for inference results in a deviation of the owed trajectory from the real data distribution, impacting the quality of generated samples. 7. Complexity. The proposed phased consistency model, PCM, introduces additional complexity in the form of multiple sub-trajectories and boundary conditions, which may increase the computational cost and training time. 8. Adversarial loss instability. The adversarial loss introduced for enforcing distribution consistency may lead to training instability and potentially corrupt the generation results, especially when combined with standard GAN training. 9. Sensitivity to negative prompts. The model's sensitivity to negative prompts may vary, affecting the ability to generate diverse and accurate results based on different input prompts. 10. Sampling randomness. While introducing randomness in sampling can help alleviate unrealistic objects or shapes, it may also introduce variability that could impact the consistency and quality of generated samples.